Problem 3.99. In this problem, water, considered as an inviscid, incompressible fluid, flows steadily as shown in the figure below. We need to determine the value of H inside of the manometer. Okay, in order to solve this problem, we are going to label the points that we're going to use. So we're going to take this to B1 and this point over here to B2. And then we're going to make a table that has the information for each one of the points. So we have point 1 and point 2, and we have pressure, velocity, elevation, and area. Okay, we're going to use different labels. So we're going to take this 1 feet to have a diameter D, and this one we're going to have lowercase d. We have different elevations. So we're going to take this one to be H1. And then notice that we have this elevation from here to here to be H2. Okay? And that's what we're going to use. Pressures at point 1 and point 2 are unknown. The velocity at point 1, it is unknown. The velocity at point 2, because of the way that the tube is immersed, it becomes a stagnation point. Therefore, the velocity is 0. We take the elevation at point 1 to be 0, so that the elevation at point 2 is simply going to be H1. And the area at point 1 is going to be pi capital D squared over 4. And at point 2 is going to be pi D squared over 4, lowercase. Okay, so we're going to start with Bernoulli equation. Notice that we cannot use continuity because one of the velocities is equal to 0. So we're going to use Bernoulli's. So we use Bernoulli's between the 2 points, and we write P1 plus 1/2 rho V1 squared rho V1 squared plus gamma Z1 is equal to P2 plus 1/2 rho V2 squared plus gamma Z2. Now let's cancel out the information based on the data that we have in the table. Velocity at point 2 is equal to 0. The elevation at point 1 is equal to 0. And then everything else remains. So we're left with P1 minus P2 is equal to gamma Z2 minus 1/2 rho V1 squared. Okay. Now what we're going to do is we're going to do the elevation. And we're going to calculate the pressure difference using hydrostatic pressure. So we start at point 2. So we say P1 is equal to P2. And then we go up, so it's negative. And we go up to this point over here. And this point, it is surrounded by, it's filled with water. So it's gamma of water times the elevation from point 2 to this point is going to be H2 plus H. Then we go from this point to the bottom one from air. Go positive because we go down. And this is gamma of air. And gamma of air times H. And then we go from that point to point 1. We go down, so it is positive. And we go gamma of water, the elevations of H2 plus H1. Okay. Then what we have over here is P1. So when we write P1 minus P2 is equal to minus gamma H2 minus gamma H plus gamma of air H plus gamma H2 plus gamma H1. And notice that the value for H2 cancels out. And we're left with the elevation H of the manometer and the difference between the 2 points. So we write P1 minus P2. Let's factor out H in this case. So H is going to be equal to gamma of air minus gamma. And then we have gamma H1. And remember that C2 and H1 are the same based on the table. So physically, we know that the pressure differences using Bernoulli and using hydrostatic pressure are the same, so we could make these two equations equal to each other. So we said gamma C2, which is minus 1/2 rho V1 squared, has to be equal to H gamma minus gamma air minus gamma of water plus gamma H1, and as we said, gamma H1 is equal to Z2. So notice that in this equation, both of these quantities cancel out. Okay, and we're left with our expression for H. H is equal to minus 1/2 rho V1 squared divided by, so we're going to rewrite this. This is going to be negative gamma minus gamma of air, so that this negative and this negative cancel out. So we're left with 1/2 rho V1 squared divided by gamma minus gamma of air. And that is the expression that you're going to get for the value of H. Now that we have the expression for H, we're going to substitute the values after we use the information given. So we have V1, we could calculate V1 using the volume flow rate. We know that the volume flow rate is equal to the area and the velocity at point 1. Therefore, the velocity is equal to Q divided by A1. Velocity 1 is going to be Q, which is 4 feet cubed per second, divided by the area, which is pi over 4, times the diameter, 0.5 feet square. That gives us a velocity of 5.09 feet per second. Okay, so now we have the velocity. The specific weight of air is significantly smaller than the specific weight of water. It's about 10,000, about 1,000 order of magnitude smaller than the water. Therefore, at this moment, we could neglect it. We could assume that is 0 compared to the value that we have for the one of water. So we're going to neglect it. This allows us to write this density, V1 squared, and this is as density times G, so that the density cancels out. If we substitute now the value of the velocity calculated, we find that the elevation is equal to 0.403 feet. Once again, we were able to do this because the ratio between water and air, it's about 1,000 times larger, and that's what allows us to get rid of or neglect the value of the specific weight of air.